things fall into place. Superposition.
Hey y'all, how's it going? Introduction to Geology here, Carlton Mueller, and today we're going to be talking about Steno's principles of stratigraphy, also known as Steno's laws. You might think of these as the laws of geology or the rock laws, whatever you want to call them, but these are kind of going to be introductory, and we're going to be using those principles of stratigraphy to perform a geologic cross-section analysis, right? So to take a slice out of the earth, view it from the side, and look at the subsurface and determine the relative timing of events based off of that cross-section. We're going to be using an analogy of a layered cake for our presentation, so that's going to come up over and over again, so just be expecting that. And your student learning objectives are you will be able to define and apply Steno's principles of stratigraphy to construct the relative timing of events of a geologic cross-section. Steno's principles of stratigraphy are used to determine the relative timing of geologic events. Steno's laws consist of the law of superposition, the law of original horizontality, the law of lateral continuity, and cross-cutting relationships. So our first analogy here to the layered cake, geology is like a layered cake, tasty learning. Which layer is poured/formed first in a layered cake? The top layer, the middle layer, or the bottom layer? Well, when you pour in the batter, right, you pour it into a pan, and so it has to form a bottom in order for things to form on top of that bottom, right? Which means that the oldest thing is the thing that went in first, which would be the thing on the bottom, right? So the layer that poured or formed first in a layered cake is going to be C, the bottom layer, right? That seems pretty straightforward. Well, similarly, the principle of superposition states rocks form in layers with the oldest on the bottom and youngest on top. You'll see we've got two cartoon schematics depicted here. On the left, the oldest, number 1, right, is on the bottom, and the youngest, number 7, is on top. Sedimentary rocks form. They form in nice packaged layers, right? Those layers accumulate on top of other layers, and so on and so forth. But in order for something to form, there has to be something below it, right? So the oldest thing is going to be whatever rock layer is at the base. You'll see we're on the right, though, there's always an exception to the rule. Don't we love that? On the bottom right, you'll see time 1, and then you'll see time 2, where we have some kind of reverse fault system going on here. We have the right side from B is being thrown up on top of A, right? And then you're going to have 3, which is probably where we're looking at it in modern day. And so you'll notice down below 1 at the bottom is the same as off to the left. But then we had this fault, this reverse fault occur, and then in modern day, you'll see if we were to stand at the top, let's just say, right here, and we go down, youngest, okay, things are getting older, things are getting older, things are getting older. Oh, what? We're back into the green again, and the blue again, and the purple? That doesn't make any sense, right? Well, that's because there was a reverse fault here that threw B up onto A, right? And so because of that, this is where it can get a little wonky. But, this is an intro, so hopefully you're not going to be seeing too many things like that. So our second analogy to a layered cake, layers in a cake are formed horizontally, vertically, or angularly. Well, based on the picture to the right, those look like horizontal layers to me. So I'm going to go with that, horizontally, right? Okay. The principle of original horizontality states rock units form horizontal to the Earth's surface. So rock units are formed relative to their depositional environment. Okay. So the way that sediments settle and stack, they're going to pile up based upon the topography or the surface, right, that they settle onto. So another way to think of this is sedimentary rocks are formed flat, and if they are not flat, then something has happened to tilt those rocks, right? So in the top left, you can see that, for the most part, we've got these really nice packages, right? Look at these. These are nice packages, nice little rectangles. Everything's where it's supposed to be. There's a little bit of an angle, sure, but that's just because of, the beach and the environment that they formed. Doesn't look like it's a perfectly level surface, but it looks pretty close. So we can take that. Now you'll notice down here, though, we've got two scenarios going on. We've got, see in the middle here, we have this squiggly line. This is an unconformity. Hold on to that thought. We'll get back to that in a bit. It's basically annotating that there's a break in geologic time. So below that and above it are two different scenarios going on. Above it, we have all these beautiful, nice rectangular packages again, right? Just like above with the beach. But then you get to this squiggly line, this unconformity, and it's an angular unconformity. And you'll see that all of a sudden the rocks are tilted. They're not horizontal anymore. I mean, they still have those really nice, rectangular packages, but they're at an angle to the rocks that they come into contact with above them, right? And so if all sedimentary rocks form horizontal to the Earth's surface, and these rocks are tilted, that means something has had to have happened after they were formed. We'll get back to that later. Question 3. When you cut a layered cake, the void in the cake used to be filled with A, the same kind of cake layer that was there before the cut, or B, a different cake layer than was there before the cut. Well, we're cutting a slice of cake out, so a layered cake, right? So the layers should be all the same all around the cake. And if we cut it out, that means we were just taking those layers out, right? Okay, so it's the same cake, right? That would make sense. There wasn't a different cake there before, right? So similarly, again, the principle of lateral continuity states sedimentary rocks form across large areas at Earth's surface, just like our layered cake, right? Here on the left, we've got a cartoon schematic, and all we're saying with this lateral continuity is that this layer right here used to be connected and is the same as this layer over here, right? Now, sedimentary rocks are reflective of depositional environments. Think of the beach. That's a depositional environment, excuse me. Right? So we've got the beach is pretty big, right? So if sandstone covers the beach and it spans the whole beach, it probably should be connected, right? So really all of these should be connected, right? This used to be connected, this used to be connected, same here, so on and so forth, right? But they're not anymore. And there's this giant scoured surface, this face looks like it's almost been cut out of what used to be there, right? Well, that's because it was. This looks to me like some kind of channel, probably from a river or creek or have you. And what happened is it eroded, so it broke down the rock that was there, and it carried it away, right? It weathered it, it broke it down, it eroded it, it moved it away from its initial location, and then it transported it, the transport mechanism being the river or creek itself. So similarly, over here on the right, you'll see kind of a bit more of a advanced version, but it's the same exact thing, right? This sandstone right here, look at that. That sandstone used to be the same. And this is what, some kind of siltstone, probably, right? Yeah, some kind of siltstone. That siltstone used to all be connected. I wonder why it's not anymore. Well, we've got that scoured face again, probably some kind of channel cut, right? Once again, some kind of water system incising down and eroding the material there. Question, can you cut a cake if it hasn't been baked yet? Wow, that's pretty philosophical. I don't think you can cut something that doesn't exist. Something has to exist in order for it to be cut, right? You can't cut a cake if you haven't baked it yet. There's no cake to cut. Okay, so no, you definitely can't cut a cake if it hasn't been baked yet. You need to bake the cake first, right? Okay, similarly, again, the principle of cross-cutting relationships states sedimentary rock cut by another geologic feature is older than what is cutting it. Perfect example here on the left. Like we talked before, we've got the law of superposition and original horizontality going on over here. That's great. Oldest, 1. Then we got 2. Then we've got 3. And then we've got 4. Okay, well, what about this youngest? Well, that must be 5 because it says youngest, right? Well, if it didn't say youngest, let's think. It's cutting through all these other layers, right? It's like it's inside of those other 1, 2, 3, and 4, those sedimentary units, right? Okay, so if it's inside of them, then those things had to have been there for it to get inside of them, right? or for it to be here, it's a magma dike, right? So in order for that magma dike to slowly make its way to the surface, right? Okay, so that must be younger, because also notice the contact where youngest ends is at the surface, right? Where it ends, where the cross-cutting feature stops, is its age. So that means that youngest here, okay, it's at the surface. Okay, so it's younger than everything because that's where it ends. If there was another rock here, let's just make it up and say that there was. Let's say that there's number 5, right? Okay, if that was the case, well, first off, this wouldn't be number 5 anymore, but you're ignoring that, so this isn't 5. But what we'd have here is we would say, okay, well, the youngest ends between the boundary between 4 and 5. So it would go in order, it would go number 4, then youngest, and then 5. So wherever the contact is its age, okay? Similarly, on the right, we've got another example, right? Okay, so let's go look over there. We got CBA, DE. Okay, well, CBA look like just normal sedimentary rock layers. So youngest to oldest, excuse me, youngest to oldest. Okay, well, oldest is going to be C. Okay, and then probably something like B, and then A, right? Law of superposition, oldest on the bottom, youngest on the top, and original horizontality. These all look great. Well, now we've got D and E. It looks like D goes all the way to the surface, and so does E, right? D goes to the surface, and E goes to the surface. That's not helpful. Well, what about D is offset right here, right? Okay, well, that's kind of weird, right? Why isn't D connected? Okay, well, E is cutting through D, right? So D used to be connected, and then a fault occurred, and then the fault caused offset, and now that you're witnessing that in this cross section. So D is being cut by E, so that means D, and then E would be the youngest, right? Okay, that seems pretty straightforward. Lastly, we've got unconformities. Remember I talked about those earlier? I think it was the original horizontality side. So unconformities signal missing periods of time and are represented by a squiggly/wavy contact between geologic features. I want you to notice that in this left diagram, right, we've got E and K right here on the top 2 layers, or E and K. And do you notice how E and K have a straight line between them? Okay, that's a sharp contact, and that checks out. That means no time is missing. That means it's accounted for in the depositional environment. Look below K, though. K has a squiggly line attached to its contact with all other units. Squiggly wavy contact, huh? That sounds like an unconformity. What type of unconformity is? Well, there's 3 different types. So you'll notice here on the right side, over here, you have K in contact with M. Now, M is cross-cutting through a bunch of things, and it looks like it's some kind of igneous magmatic pluton. Okay, it's just a giant magma body, right? So it looks like that was in place, and it's touching K, and there's a squiggly line. We do not want igneous and metamorphic rocks touching sedimentary rocks. That is a big no. Big no. Okay. Why is that? Well, if we have sedimentary rocks, think of the beach. If you're at the beach and you were sitting there, and then all of a sudden magma started to come up and you just had lava spewing up all over the beach, well, that would be like a pretty big change, huh? Right? I don't think you've probably ever seen that. I mean, I sure haven't. So, we want our depositional environments, or where these sedimentary rocks form, to remain relatively the same. And if they don't, then there had to be some kind of drastic change in the tectonic conditions or something like that in the area, right? So you'll notice the first 2 letters of nonconformity, no touch. Igneous rock, metamorphic rock, no touch, sedimentary rock, okay? That's number 1. Number 2, angular unconformities. We talked about this one a little bit, right? We talked about this. You'll notice that here, I and C, right, they're at an angle, maybe I should say 45 or something, or maybe more, to K. Well, that's not right. E and K aren't at an angle. They're forming horizontal to one another. Okay, so they're forming it. Their contact with K is at an angle. So there must have been something that happened to make them occur at an angle, like we talked about before, right? And then the last one is just a disconformity. So, and I don't see one on here. So we'll make one up. Say between K and E, it wasn't a sharp contact, but it was also like a squiggly line, right? Squiggly wavy line. Well, E and K are both sedimentary rocks, and there's a squiggly line. So what that means is that there's just been some kind of erosion or uplift, and there's a missing gap in time, right? So this is all relative dating, right? So for example, maybe you had a fossil in E that's 200 million years old, and in K, rock unit K, you had a fossil that's 300 million years old, right? So we can tell that, okay, there's some kind of missing chunk of time here. I wonder what happened. Some kind of erosional event, most likely. So now that we've gone over Steno's principles or Steno's laws, let's use them. Let's apply them. Let's make them a tool that we can harness. So I want you to analyze this geologic cross-section and note that there are unconformities in here. So try to list the oldest to youngest events, including the unconformities. You'll notice the unconformities don't have a letter on them. Okay, I think I see about 5 unconformities. Let's see if you can find the fifth one. It's kind of hidden. All right, well, hopefully you took the time to look at that. And if you haven't, please just pause it, right? But with that being said, let's get in here really quick. So let's start off. I like to look for the thing on the bottom. There's two things on the bottom. We've got E and we've got A. Okay, well, A and E both look again like that igneous rock, like they were depicted before. But more importantly, A is cutting through a bunch of things, and it tops out here in between J and N contact, right? Okay, and it's, you know, it's all like this amorphous blob, okay? All right, well, that looks like some kind of Pluton again, and that's not the oldest for sure, because it stops at N. Okay, well, E does not go anywhere, and it has everything on top of it. That's probably like the crystalline basement rock, E. So E is probably going to be the oldest. And then we have an unconformity here. Okay, well, that makes sense. Looks like we've got some kind of sedimentary package above, right? There's original horizontality working for us. G, L, and C are all horizontal to one another. And they're, you know, formed horizontal atop E. So just using the law of superposition, right? We're going to have an unconformity. Notice we got the squiggly line, right? So we've got the crystalline basement, and then we've got sedimentary. So that's a non-conformity, right? No touch. So we'll just put unconformity, non-conformity specifically. And then we're going to have G, L, and C, right? Because those just stack up. Law of superposition, original horizontality, all is great. Now we've got to look. We've got another unconformity between C and M. We also have a fault here, H, that stops at M. Interesting, right? I'm going to go ahead and say that the faulting is it looks like M and D and J, that looks all original horizontality, superposition-esque, right? So those are stacking up like sedimentary packages. That's great. So this looks like a sedimentary rock touching a sedimentary rock, and there's some kind of missing gap in time, an unconformity, right? So I'm going to go ahead here and say that H faulting probably occurred, right? And that's probably why there's missing time, is because a faulting event caused a lot of erosion. And now we've got a nonconformity, which is not a nonconformity, a disconformity, right? Disconformity, sedimentary, touching sedimentary, we are missing time. So an unconformity, specifically a disconformity, and then we're going to go M, D, J. Okay, we've got J, and then we've got another squiggly line, and we've got A. Okay, well, that's interesting. Well, let's go with A, because it stops at the contact, right? And then A is an igneous rock touching N, so that's a no touch, nonconformity. Okay, and then it looks like we've got N, and then K and B. Those all stack up nicely. Now, they're at an angle to F, though. So it looks like, and there is a squiggly line, right? So we've got another angular unconformity, and then F, and then the fifth unconformity is the surface as this sediment is still being deposited and it hasn't yet formed a rock. Well, let's do another. Use Steno's principles of stratigraphy to determine the relative timing of geologic events. Well, we've already got this under our belt now, so let's get to it, right? Please feel free to pause it and come back to this. But we're going to move ahead, and we are going to say that the things on the bottom are, looks like D, shale D is at the bottom, right? D is at the bottom. C goes from the bottom, but also up to the surface. So we'll figure that out later. H is at the bottom, but it's an intrusion. So first off, it tells you, but also it's got this cross-cutting relationship. It's cutting through these folded layers, and it tops out at K. Okay, so we should probably come back to H whenever we get to unconformity I and conglomerate K. So for now, we're going to just start with, superposition again, oldest on the bottom, D, and then A, E, and then J, right? And those layers were formed, and look at how they're all folded. Okay, so they're all weird, wavy shapes and angles, but they're supposed to look like F and K and G above them, right? They're supposed to look like horizontal, nice packages. Okay, so some kind of folding event must have happened after those were deposited. All right, now we get to unconformity I, intrusion H, and all that fun stuff. Okay, so we're probably going to go with intrusion H, right? Because it ends at unconformity I. Then we've got unconformity I. And then we've got conglomerate K, F, and G stacking up nicely. And then intrusion C and erosion B are at the surface, right? Well, I know that erosion is always going to happen forever. Okay, well, that's good to know. So with that being said, then erosion is always going to be the youngest thing. Always. It's happening every second, which means intrusion C is going to be before that. So overall, those were Steno's principles of stratigraphy, or Stenos' laws. And I hope that this was informative and you can use them as a tool to analyze geologic cross-sections, the subsurface of the Earth, and to determine the relative timing of geologic events. Thanks so much.